The name of this video is Shell E from V. Let us consider a charged shell with a surface charge distribution with constant density small sigma equal the total charge divided by the surface area, which is 4 pi capital R square if the radius of the shell is capital R. Let us sketch this shell here. This is our shallow charge. The center is right here. And this is the radius capital R. As always, we choose, in this case, a spherical coordinate system, where this is the r-axis, var phi points into the page in this direction, whereas theta is oriented in this fashion. So that in this case, if this angle here is an angle d theta, this is a charge point capital Q, and this again is our radius R. Because of symmetry arguments, see one of the home assignments, with respect to both var phi and theta, the only degree of freedom of this problem is small r. That is, we can pick any point, let's say a point on the axis here, R, this point capital P, and if we solve the problem for that point capital P, we basically solved it for any other point in space. Okay. This again is due to the symmetries. With respect to both var phi and theta. Let us indicate this distance. Let us do it actually in yellow, in orange, so it's more clear. This distance, we call it Greek z, which is equivalent to r, the norm of the vector rqp. Note that this quantity z can also be written by means of the Cosine Theorem as the square root of capital R square, this vector, this segment, plus small r square, this distance here, minus 2 times capital R small r cosine of theta, power of 1/2. A generalized Pythagorean theorem with a given angle theta oriented in that fashion. Okay, so with this in mind, we know that on a surface as such, an infinitesimal area element, dA, can be obtained by multiplying r d theta, capital R d theta. Then we multiply this times r sine theta, which is this distance, and this distance we need to rotate it by a var d phi. So r sine theta times d var phi. Okay, this is our infinitesimal element on a surface in a spherical coordinate system. Okay, given this infinitesimal element, we can calculate the infinitesimal potential due to this element, which is characterized by a charge dq given by sigma dA. Since it's so simple, we can straightforwardly integrate to find the potential V at any point capital P, which eventually becomes r. That's the only degree of freedom. This is given by 1 over 4 pi epsilon naught. We then need to integrate, so we are integrating d var phi from 0 to 2 pi. Whereas theta, we need to integrate it from 0 to pi, not to count 2 times whatever is included in these two here. So d theta, we are integrating dq divided by rqp. Okay, dq divided by rqp because that's the Colombian time potential, integrating with the superposition principle. So obviously, here we obtain the charge, which is d var phi d theta sigma r square, capital R square, times the sine of theta. We are integrating here in theta. And this has to be divided by the distance, which is nothing but z, the Greek z. Okay, or RQP if you want. Okay, first glance, this may seem a pretty complicated integral. Actually, it's trivial. Of course, this first integral just gives us a 2 pi, so pi and pi cancel out, and I obtain a 2 here. So if I am to solve this integral here, we obtain sigma over 2 epsilon naught. This is what is left over after integrating with respect to bar phi. So we get sigma over 2 epsilon naught. What about this integral? Well, if I take out a capital R divided by a small r, so I know that I take one of these two r out, so there is one r left. And if I look carefully at this expression here for Greek z, I notice that if I were to perform the derivative with respect to theta of this quantity, we obtain 1/2 times minus 2, which gives us a 1, times r, okay, which is this r, and the other r I obtain from this derivative. Small r, which has to cancel out with this r here, so this r from the derivative cancel out. The derivative of cosine theta is minus sine theta, so with the minus sign becomes plus sine theta, which is what we have up here. 1/2 minus 1 becomes minus 1/2, which is what we have in the denominator. So the derivative of this object, with the caveat that we need to take out capital R over small r, actually is nothing but this integrand, okay? And so the integral is nothing but this object here. So we simply need to compute the Greek z from what angle? Theta goes from 0 to pi. In order to understand this integral, I like to do it geometrically, and that's what we are about to do here on the new panel. Okay, so how do we find the solution geometrically, which I think is a very elegant, very beautiful method to find the solution? Well, let's distinguish between two regions. As always, region 1 is for each point r in the domain from capital R to plus infinite. Note that I already here included capital R. And why can I do that in the case of the electrostatic potential, whereas in the case of the electrostatic field I cannot? Simply because I know that the electrostatic potential is one of the properties, has to be a continuous function. So I can include all boundaries. When I stitch it up, it has to be continuous. So we can right away put it in there. Okay, in this case, let's make a simple sketch here. So we retake again this shell of charge, and we want to understand what is the meaning of z for theta equals 0 pi in this case. So the way we do it is as follows. Okay, this is our shell. This is the origin O of our coordinate system. Okay, this is the origin here. Okay, this is our point capital Q. On R, this is our point capital P. This quantity is Z. This angle is theta. So what happens, and of course this quantity is capital R, and this quantity is small r. So what happens when theta is equal to 0? Let's do this in orange. When theta is equal to 0, I squeeze this down, so I'm taking this point, and I move it all the way up, which means this point eventually becomes this point here, which means this segment here is my actual z. So this is z, in this case, theta equals 0, okay, in orange. What is this quantity here? Well, this quantity is nothing but small r minus capital R. What about in red? Actually, let's do it in yellow. What about the case theta equal pi, which is the other limit here of integration? And in this case, z, we are in this yellow scenario here. So in this case, we are going all the way with theta to the opposite side here, which means this point is going all the way here. And so the quantity z becomes all this quantity here, okay, which is nothing but small r plus capital R. Small r plus capital R. Great. So these are the limits of integration in the region 1, which is outside the shell, if you want. So in this case, the electrostatic potential V at any point R of this type is simply given by sigma over 2 epsilon naught, which multiplies capital R divided by small r, as we see here, times R small r plus capital R minus small r minus capital R. This is very simple algebra. Small r cancel out. We obtain 2 times capital R. 2 and 2 cancel out. So I obtain capital R squared over small r. So this gives us sigma over epsilon naught capital R squared divided by small r. If you want to use this definition of charge here, this we already know what to expect outside the shell. We expect a Colombian type potential. So it has to be, you can do the algebra, but obviously it has to be a single point like charge, as if it were a single point like charge. And so it's 1 over center concentrated focus here in the center. And so it's nothing but Q divided by R, okay? Which is a Colombian type potential. Okay, so this is the first part of the solution, which means outside the sphere. What about inside the sphere in region 2? So let's now focus on region 2. So we take any r in the domain from 0 to capital R included. And again, as here, we can safely already here include the capital R because we know that V has to be a continuous function, okay, which we will verify in a few minutes. Okay, in this case, again, we want to repeat the same argument. This is our shell, centered in O. This time, however, we want capital P to be inside this on this axis. So we want it to be, let's say, here. This is our point capital P within the shell itself. So if this one is our point capital Q, this quantity is our quantity Z. The radius, of course, is always capital R. And so in this case, the angle theta is this quantity here. Okay, and this is the radius capital R, okay? Okay, so in this case, what happens when theta is equal to 0. We are in the second region for theta equal to 0. Well, grid z in this case, we do again in orange in this case. So this means that theta goes to 0, which means this point goes all the way to here, which means grid z becomes this quantity here. Okay? So it's this quantity here we're looking at. So this quantity clearly is capital R minus small r. Okay, the other limit of integration is when theta is equal to pi. Grid z in this case, let's do this in yellow, as here. In this case, we end up from this point all the way to the bottom here. Okay, which means my quantity z becomes, instead of this quantity, the whole quantity down here. Okay, and so it becomes capital R plus small r. Great, so now we have our limits of integration here. So here I remind you that the limits were, this was the orange one, whereas this was the yellow one. Whereas here, this is the orange and this is the yellow. Okay, so in this case, we can readily find the electrostatic potential V at any point R, similar to what we've done there, obtaining in this case sigma over 2 epsilon naught, as there, capital R over small r, times in this case, the difference between capital R plus small r minus capital R minus small r, simple algebra again. This gives us, as a result, sigma over epsilon naught capital R. And if again you have to use this definition of charge here, so I inverted to find as a function of q, well, then we obtain simply 1 over 4 pi epsilon naught q over capital R. Great, and in fact this is a good sign, because we know that in the limit for small r which goes to capital R, we obtain the same result, which is what we want to stitch together. All right, so now we can summarize our electrostatic potential, and we know that V of R is equal to either 1 over 4 pi epsilon naught q over capital R for R in the region within, which means from 0 to capital R, or 1 over 4 pi epsilon naught Coulombic type q over small r for R included from capital R to plus infinite, Coulombic type potential. So in this case, we can plot this potential. So we do the usual plot here. This is our sphere. This is the center here. This is the r-axis. And this one is the v-axis in this case. Okay, with center here. At this point, the origin. The radius, of course, is capital R, as always. And here, we end up at this point here. All right. So let's plot it. Inside has to be constant with this value here, all the way to this point. And from this point on, it needs to go down as 1 over R. Okay? So here is proportional to 1 over capital R constant, whereas here is proportional to 1 over small r. Okay? Great. So that's our plot. Now, if we formally perform the limit for small r that goes to capital R minus, we need to use this solution here. We are inside of V of R. We obtain 1 over 4 pi epsilon naught of this constant, so Q over capital R, which is exactly the limit. Is exactly the same as the limit for small r that goes to R plus. So now we use this solution, and so this becomes capital R of V of R. So we obtain exactly the same solution when we use that. So this implies that, at least in this case, we verified that the V of R is a continuous function for any point from 0 to plus infinite, including at this boundary. All right, great. The continuous function we just verified. This was one of the properties we discussed in the beginning. Now that we know that, the next step, which is interesting to eventually do here, is to find, the final aim is always to find E, the electrostatic field, from the potential, okay? So how do we find E? From the general definition of E, obviously, we can obtain that E is equal minus the gradient of V, but it only exists along the R direction. So in this case, in general, it should be the partial derivative is the gradient in a spherical coordinate system, but only with R. So V of R along the R direction. But again, this partial derivative, in this case, we can simply call it a total derivative because that's the only variable that we have. And so what we obtain here, similar to this, we obtain in this case 0, because this is a constant function. So vector 0 in the region R from 0 to capital R. Okay, in this case, we want to be careful with this bracket. Let's keep it open for a minute, okay? Because we know that this is a field, and it's an electrostatic field for what case? Case 2. This is case 2. Why is case 2? Because we have a surface charge distribution. So this surface is actually case 2 of Maxwell's equations. Great. So if it's case 2, we need to be careful about continuity because we already know that it's discontinuous. Let's verify it. In fact, when we perform the derivative with the minus sign of this quantity here in the region outside, obviously we obtain Coulomb's law. Okay, because we pick a minus sign from the derivative, but we regain it from this minus sign here from the definition. So here we obtain 1 over 4 pi epsilon naught Q divided by R squared from the derivative, and again, R minus 1 gives you minus sign, it becomes plus in the UR direction, and this is for R, from capital R all the way to plus infinite. Now what happens at these boundaries here? That's the interesting part. At these boundaries, there is a discontinuity of the first kind. What is this discontinuity? Well, if we substitute inside this Q the definition of given up here, so sigma times 4 pi capital R squared. Obviously, 4 pi and 4 pi cancel out. Okay, so then we do the limit for R that goes to capital R. Okay, so we obtain R squared. So this R squared cancels with this R squared. So these two R squared in the limit also cancel out. And so we are left with sigma over epsilon naught. So the discontinuity is sigma divided by epsilon naught. And guess what? This is exactly the same kind of discontinuity that we obtained in case 2 of Maxwell's equations, which I remind you is nothing but the normal components, E1 minus E2, the difference of the normal components I project along n to 1. This has to be equal to sigma over epsilon naught. Gauss's theorem in the surface case, so case 2, okay? So finally, we can also verify that if we perform, we should have done this up here. So if we do the limit for r that goes to plus infinite, we obtain as a result that v of r is equal to 0. So normal conditions in infinity. In fact, it goes to 0 at infinity, as you can see up here. So in this problem, to summarize, we considered again a shell of charge with a constant density sigma with radius capital R. We wanted to find V, the electrostatic potential associated with this shell, in a spherical coordinate system. So we did that by integration. The integral actually is easier than the one we used to find E for a shell using Coulomb's law and the superposition principle, that is integration. So by means of this simple integral, which was really trivial, we could solve it geometrically, distinguishing between two regions when capital B is outside or inside the sphere. By doing that, we obtain this solution for the potential, which is constant, Q over R inside the sphere, and is 1 over R, it goes as 1 over R, Coulombian type outside the sphere. In the limit to infinite is regular, it goes to 0. It is a continuous function, which is something we wanted to verify, so it's C naught. It's a beautiful continuous function. Now we can find E by means of the definition minus gradient of V, which in 1D in this case, because it's only a function of R, is super easy. And we obtain a discontinuity of the electrostatic field. So while V is continuous, the electrostatic field is not, is discontinuous. In fact, the electrostatic field will look something like this. It's 0 here, open dot, and then there is some open dot somewhere, and then it goes as 1 over R squared. A little bit stricter than that, okay? Which we already plotted before. That's for the electrostatic field, okay? So this is for E. That's what I plotted there. All right, that's it.